Alright, in this video we are going to look at 5 characteristics common to all waves. So it doesn't matter if they're electromagnetic or mechanical, it doesn't matter if they're transverse or longitudinal. All waves have these 5 characteristics. They have amplitude, wavelength, frequency, period, and velocity. Amplitude is a measurement of how much energy a wave carries. It's the one thing that is most often related to the amount of energy that a wave carries. The higher the wave, the more energy it has. The lower the wave, the lower the amplitude, the less energy the wave has. In transverse waves, it's measured from the equilibrium position to a crest or a trough, so measured either up or down. So every line, every arrow you see drawn in that wave, A, B, C, D, and E, would all be a measurement of amplitude. And they'd all be the same, provided that this wave is not losing any energy. Most common mistake students make when they're measuring amplitude is to measure it from a crest all the way down to a trough. We don't do that. It's always measured from the equilibrium position. So you can go from equilibrium up, or you can go from equilibrium down. Waves of different amplitude, transverse waves of different amplitude, have different heights. So when we look at these 3 waves side by side, the difference between these 3 waves is amplitude. This wave has a very small amplitude. This one has kind of a medium amplitude. This one has a large amplitude. And again, it's a measurement of how much energy that wave carries. The higher that amplitude, the more energy it carries. So not only can we say this wave has the highest amplitude, but this wave would also have the most energy. Again, this one has the smallest amplitude, so we can assume it has the least amount of energy. In longitudinal waves, it's very difficult to illustrate amplitude. These are pressure waves, and the amplitude just ends up being the difference between normal pressure and high pressure, or normal pressure and low pressure. Because in theory, as a longitudinal wave travels, it should increase the amplitude the same amount that it decreases the amplitude relative to the normal pressure. This is one way that I've seen it illustrated. These are tuning forks. They're vibrating back and forth, pushing left and right to make the compressions and rarefractions. Those are my compressions, in between my rarefractions. This is illustrating a low amplitude because we can see in the high pressure areas there's not a whole lot of particles. This one represents a higher amplitude than the first wave, and it does that by showing us more particles in those compressions. In other words, it's saying we've raised the pressure here, but we haven't raised it that much. Here it's saying we've raised the pressure and we've raised it a lot more. So that's low amplitude, that's high amplitude, illustrated in a longitudinal wave. Means the same thing. The more amplitude it has, the more energy it carries. The lower the amplitude, the less energy it carries. So we go back to this. This wave would be carrying less energy than that wave. Wavelength is the length of one complete wave cycle. It's measured from one point on the first wave to the same point on the second wave. And it really doesn't matter what those points are. The most common way to do it in a transverse wave is to measure it from crest to crest or trough to trough. One point on the first wave to the same point on the next. One point on the first wave to the same point on the next. Doesn't matter if you do it that way, it's just those are the more conventional ways of doing it. So there are actually 4 segments here, A, B, C, and D. A runs from here to here. That is a wavelength, measured trough to trough. B runs from here to there. Again, a wavelength running trough to trough. C runs from there to there. Again, a wavelength, this time measured from crest to crest. And D runs from there to there. Again, a wavelength measured crest to crest. All of those should be the same, provided the motion of my wave is constant. Again, that's just the conventional way to do it. You can literally measure it from any point. So we can go from where the crest begins to where the next crest begins. And that would be a wavelength, and it would be the same as all the rest. We can go from halfway down to the trough to halfway down to the trough. Measure that, and that would be a wavelength. And again, it would be the same as all the rest. So it's 1 point on the first wave to the exact same point on the next. That's the true definition. Same definition applies to longitudinal waves, but again, there's a convention here. And the way it's usually done is to measure the length of one compression and one rarefaction. So this is a compression, this is a rarefaction. And if we start at the beginning of the compression and go to the end of the rarefaction, we've got a wavelength. But again, it can be measured in any way. We can go from the beginning of a rarefaction to the end of a compression. That would be a wavelength. We could go from the middle of this rarefaction to the middle of that rarefaction, and it would be a wavelength. Again, technically, all wavelengths. Any point on the first wave is the exact same point on the next. That is wavelength. Frequency is the number of waves that pass a fixed point every second. It's like standing on a dock and counting the waves as they roll by. It's the number of waves that roll by you every second. It's measured in a unit called Hertz, abbreviated HZ. It's one of the few metric units that have a two-letter abbreviation. It is capitals H, lowercase z, Hertz. And it's basically 1 wave per second. 1 Hertz would be 1 wave in 1 second. 50 Hertz would be 50 waves in 1 second. Again, it's the number of waves that pass a fixed point every second. It is related to wavelength. If everything else is constant, specifically if velocity is constant, short waves will have high frequencies, long waves will have low frequencies. So the way we draw a high frequency wave is by making our wavelength short. And this is a transverse wave, so again we measure from either crest to crest or trough to trough most often. And we can see we have a short wavelength there. Short wavelength means high frequency. On the second wave, again measuring it from crest to crest, you can see my wavelength is much longer. Longer wavelengths give us lower frequency. So as the wavelength goes down, the frequency goes up. That means they are inversely related. As wavelength gets bigger, frequency gets smaller. Again, we can see that they are inversely related. To calculate frequency, you use this equation. Frequency is equal to the number of cycles, or waves in this case, per second. We use the general term cycles because there's other things that have frequency. As a pendulum, for example, has a frequency. So we wouldn't want to say waves up there. We just say cycles as a general term. In this unit, because we are working with waves, it is simply the number of waves divided by the number of seconds. So a boy is standing on a pier. He counts 7 waves pass by in 18.2 seconds. We want to know what the frequency is. Again, the frequency equals the number of waves, or cycles, divided by the time in seconds. And if this time had not been in seconds, we would have to convert it. If we have minutes, we'll multiply by 60 to convert it into seconds. If we have hours, we will multiply it by 60 to get it into minutes, and then multiply by 60 again to get into seconds. So our waves, 7 waves, 18.2 seconds. It's 7 divided by 18.2. Our frequency, and again just rounding arbitrarily, is 0.38 Hertz. This is waves per second. It's really no unit on top because it's a count that's up there. Anything per second, waves per second, swings per second, whatever, cycles per second, ends up being Hertz. Again, make sure that time is in seconds or It's not yet converted. Period is the inverse of frequency. If frequency is the number of waves per second, period is the number of seconds per wave. It's the amount of time it takes for one wave to pass, again in seconds. It is the inverse of frequency. Again, frequency is the number of waves in 1 second. Period is the number of seconds for one wave. They are the inverse of each other. They're kind of flipped. So we can say if a wave has a high frequency, a very large number for frequency, it's going to have a short period. It's going to have a very small number for period. They're going to be the opposite of each other. If a wave has a low frequency, a small number for frequency, it's going to have a long period or a big number for its period. They will always be opposites of one another. To calculate period, we will use this equation. Period equals 1 divided by the frequency. It is the inverse of frequency. We could say frequency is 1 over the period, just the same. They are the inverse of one another. So if I know the frequency of my wave, I take 1 divided by that frequency. That will tell me the period. If I know the period of my wave, I can do 1 divided by the period, and that would tell me the frequency of it. So let's take a look at the question here. The frequency of a sound wave is 440 hertz. How much time does it take for each wave to pass? The amount of time it takes for one wave is the period. So period is equal to 1 divided by the frequency, or 1 divided by 440 hertz. 1 divided by 440 is 0.0023. And that will be seconds. Hertz is waves over seconds because seconds is in the denominator of the denominator. It moves up. And so your period ends up being measured in seconds. Finally, wave velocity. Wave velocity is a measurement of how fast the disturbance or the energy that's carried by that wave travels. You can think of frequency as measuring how fast the medium vibrates, how fast the medium moves up and down or left and right. Wave velocity tells us how quick that energy gets from one place to another. It's how fast the energy travels. We can use the plain old speed equation to calculate wave velocity. Speed equation is distance divided by time. So if we are given the distance that the wave travels or the energy travels, and we're given the time that it travels in, we can calculate the speed of that particular wave. So a laser beam travels to the moon and back in 2.5 seconds. That's the time. The distance to the moon is 238,900 miles. Now we're going to have to make an adjustment to one of these two numbers, because that's the distance from the Earth to the moon. That is a one-way distance. But our time is from the moon and back. So we have to go there and back for the time. So we're either going to have to double the distance so that we have the distance there and back, or we're going to have to cut the time in half to compensate for the fact we're only going one way. And I think it's a lot easier just to cut that time in half. So 2.5 seconds divided by 2 is 1.25 seconds. That way, what we're dealing with matches. Instead of having the time there and back, all we have now is the time to the moon. So we have the same kind of information for both values. So speed equals distance over time. 238,900 miles divided by 1.25 seconds. 238,900 divided by 1.25 is 191,120. And that's miles per second, exactly what we have up here in the equation. If you wanted miles per hour, you would have to multiply by 60 to get into miles per minute, and then multiply by 60 again to miles per hour. So that is almost 700 million miles per hour that light travels. Really, really fast. Now, if we're dealing with a smaller distance in light, that equation is totally impractical. If we're dealing with the amount of time it takes a light wave to travel from the lights down to your desk, that's going to make that journey so quickly, because again, 700 million miles an hour, that there's absolutely no way you're going to be able to measure how long it takes. So in those cases, what we're going to do is use a different equation, the wave velocity equation, which is velocity equals wavelength times frequency. Wavelength is abbreviated with the Greek letter lambda. W's have been used up. Lowercase w is weight. Capital W is work. If it's a unit, it's watts. W's have been used up. So instead of using W for wavelength, they use the Greek letter L. That's lambda. So just wavelength times frequency. The wavelength will provide the distance unit for your speed. And hertz will make the time unit seconds, because the hertz is waves per second. So the wavelength will provide your distance unit for your speed or velocity, and hertz is going to provide seconds. So if your wavelength's in meters and your frequency is in hertz, you have meters per second. Again, the wavelength provides the meters, the hertz provides the seconds. If your wavelength's in feet and your frequency's in hertz, your velocity is going to be in feet per second. Again, the wavelength will bring the distant unit feet, hertz will bring the seconds to the party. Let's take a look at how it works. The sound wave has a frequency of 550 hertz. And a wavelength of 0.62 meters. What's the speed of sound, or velocity? Waves tend to move in straight lines, so distance and displacement are typically the same, so speed and velocity are interchangeable here. Velocity is wavelength times frequency, 550 hertz times 0.62. Yeah, I wrote this backwards, but it doesn't really matter because we're multiplying. 550 times 0.62 is 341. Meters per second, because the distance unit will come from my wavelength, and hertz will bring seconds into the mix. Now I want to point out, this is really, really important to know. There are things that can confuse you when dealing with mixed problems, multi-step problems in this, because wavelengths and distances a wave travels will both be measured in meters. But one of them is a wavelength, the other one is a distance. Again, we have those two different equations that we can use to calculate velocity. You've got to read the question to figure out which one is which. You can have two different things that measure time. In seconds, you have periods, capital T, and you have time, lowercase t, in terms of how long it takes a wave to get one place to another. So there's multiple things that use the same units, and you're not going to be able to look at just the numbers and the units to figure out what's what. You're going to actually have to read the question, find what it is from the context, from the actual wording of the question. I do also want to point out there's more than one way to solve the problem here. I've got a frequency of 550 hertz. And I can turn that into a period by doing 1 divided by the frequency. 1 divided by 550 is 0.0018. seconds, because again, that's waves per second on the bottom. Seconds is in the denominator of the denominator. It moves up. That's the amount of time it takes for one wave to go by. Well, one wave is 0.62 meters. So if I use that as a distance, and I use this number, 0.0018, the period, as a time, I can use the old speed equation, speed equals distance over time, to find the velocity. 0.62 meters over 0.0018 seconds. And when you punch that in the calculator, you get the same answer. 0.62 divided by 0.0018 is 344.4, rounding. If I had kept all the decimal values I could, because this is a repeating number, it's 18181818. If I had carried out all those 1/8s and filled the screen, it would have been exactly 341. There's a slight difference here because of the rounding that I did. But again, same answer. There's more than one way to get there. There's more than one way to interpret that question. We can obviously use that equation algebraically, just like we can use any other equation algebraically. (1,450 meters per second is the velocity. And then I have a wavelength of 0.62 meters, and that is a wavelength because that's what it tells me. It's not a distance. I want to know what the frequency is. Velocity is wavelength times frequency. 1,450 meters per second is equal to 0.62 meters times frequency. Divide both sides by 0.62 meters to solve. Write it F equals, because that's what math teachers like. 1450 divided by 0.62. This would be 2338.7 hertz. Again, just using that algebraically. As I mentioned, multi-step problems take it to a whole different level because there's things you can mix up. So when you get to those, do be careful.